So this is a very interesting way to construct a particular scheme. But there is actually a way that you can use to generally construct schemes. So that's basically, let's go back to the blue procedure. So here, what if I imagine my A1, A2, etc. are just numbers that are going to be divided by something times delta t, right? So whatever number of delta t I want to divide can actually be included in these coefficients, right? So here I divide by 4 delta t. I can just set the coefficients to a fourth and minus a fourth. Here I'm dividing by 2 delta t. I can just set the coefficients to half and minus half. Okay, so the coefficients can actually be figured out algorithmically. It can be figured out algorithmically through a little bit of linear algebra. So let me just show you an algorithmic way of deriving exactly the same scheme without doing any error-prone hand calculation at all. All right. So this is just assuming these are just the 5 numbers. So imagine I'm only allowed to use these 5 points, and I want to say I want a scheme that is as high order as possible. What does that mean? That means if I write down the Taylor series of all these 5 terms, so I already have 4 terms written down over here, right? And the Taylor series of u of t, just the u of t, right? There is I don't have any delta t to expand on, right? So all the delta t squared terms are actually 0 because delta t is equal to 0. Okay, so basically I have the 5 Taylor series terms. So I need to cancel the first term after I multiply each term by the respective coefficients and add them together. They have to be what? 0, right? Because I don't want to approximate ut. I want to approximate the derivative of ut, right? When I multiply the second term with their respective coefficients and add together, that should be what?
1.
Should be 1 because I already divided by delta t, right? So delta t shouldn't be counted, and I'm approximating exactly this term. Okay, the third term when I add it together should be what? 0, right? So I want as many terms to be 0 after that as possible because that gives me the highest order scheme. How many terms can I expect to cancel with that? So I have 5 coefficients to play with, right? So I have to cancel the first term. That's unconditional. The second term has to add up to 1, unconditional. That's already 2 equations. I can have 3 more zeros. I can expect 3 more zeros, right? So 3 more zeros is what I'm looking for. That gives me in total 5 equations. The first equation is this: the constant term has to be zeroed out. So one equation is basically, that equation is simple, just a1 plus a2 plus a0 plus a minus 1 plus a minus 2 has to be 0, right? There is nothing on top of that. The second equation is, okay, a little bit more difficult, a1 plus 2a2, right? Because the a2 is multiplied on this, and there is a 2 on top of this. So a1 plus 2a2. a0 doesn't count, a0, because a0 doesn't have this term. And then minus a minus 1. And minus 2 times a minus 2 has to be equal to 1. Okay? And the third term is going to be half of a3 plus, half of a1 plus half of a minus 1 plus 2 of a minus 2 and plus 2 of a plus 2 has to equal to 0, right? So basically we get these 5 equations, and we can solve these 5 linear equations by what? Constructing a matrix and backslash it in MATLAB. So we'll be doing linear algebra all the time in this class. So linear algebra is really important. So the matrix we are going to get, so we have 5 equations. okay? And we have 5 rows in the matrix. Each row in MATLAB is separated by a column. Okay, so let me see. A is equal to this. So what is the first? Actually, I think it's let's say what is the first row? The first row is it's just the ones, right? It's just the 1, 1, 1, 1, 1. That corresponds to the first equation, which is saying that the constant term has to add up to 0, right? Is it clear? Like the first term, the first row should all be ones. I mean, at some point you need to, if you haven't already, you need to be able to kind of go back and forth between linear equations and matrices in a very fast way, almost like you are playing an instrument or something. Right, okay, so the first equation is basically the sum of all 5 coefficients are equal to 0. So that corresponds to a matrix row of all ones, okay? The second row has coefficients. Oh, let's figure out an order. So let's actually order from the leftmost to the rightmost, right? So this is the first variable, this is the second variable, 3, 4, 5. So let's order these unknowns to be like that. So for -2, the second term is actually -2, right? It's -2 times that unknown, plus -1 times that unknown, and plus 0. So it's actually -2, -1, 0, 1, 2. All right. Okay, you can go back to the Taylor series, but the next term is basically just the previous one squared. It's just the 4 and 1 and 0 and 1 and 4. So that's the second order term. Third order term is just the 8, no, not 8, -8, -1. Okay, so in reality, you have to actually divide by 2 on this one, and divide by 3 factorial on this one. But because they need to be 0 anyway, right? So that constant factor applied to every coefficient doesn't count. 0, 1, 8, and then 16, 1, 0. It's basically to the 4th power. All right. So that's the matrix. Any questions on the matrix? That kind of encode all the equations we want to satisfy, except for the right-hand side, which is 0, 1, 0, 0, 0. Okay, very good. Okay, so the historical moment arrives when I do A\B. So what do I get? Okay, so I get a bunch of like 3, 3, 6, 6, 7, 6, 6, 7, 3, 3. That kind of is intuitively should be something divided by 3, right? So let's see, if I multiply by 3, okay, I get 0.25. That means I should actually multiply by 12. So I get 1 minus 8, 0, 8, 1. So I have the scheme, okay? So the scheme should be, I'm running out of space over here. So let me write it on top. The scheme should be 1 over 12 delta t, because I have the 12 over here, okay? And 1 is the u of t minus 2 delta t, right? And minus 8 u of t minus delta t, and 0, which means I don't have any ut, and then plus 8 and minus 1. So plus 8 u of t plus delta t, and minus u of t plus 2 delta t. Okay, so compare that to this. I should have actually factored out the 8 with the 3 halves, but it's the same scheme. It's exactly the same scheme. All right. So no matter how high order of a scheme you want to go, you can do this algorithmically. You just get a bigger matrix, right? You just get a bigger matrix than the matrix we generated, and you can see. I mean, if you look at the matrix, look at the pattern of the matrix, you can see that you can algorithmically generate the matrix, right? You don't have to hand type it. It just goes. It just expands into each direction and expands downwards, right?
Does it mean that you always have to be kind of symmetric about it?
Very good question. No, actually, there is a lot of applications where you only can bias towards one side. I mean, in ODEs, that's often the case, and in PDs around the boundaries where you don't want to solve afterwards, that's also the case. So there is a lot of cases where you want to construct a derivative formula that doesn't involve like some grid points, and you can do that perfectly fine. All right. Okay, very good question. So this is a way to really easily design high order schemes. All right, and you should be able to do that in the future.